Time is not a human invention, but a cosmic force written in the motions of the heavens. For billions of years, celestial clocks have orchestrated Earth's entire history, from the coming and going of ice ages to the very evolution of life. By the end of this exploration, you will see our planet's story through an entirely new lens, revealing the hidden rhythms that dictate our future. We will uncover why Earth's axis wobbles like a slowing top over 26,000 years, and how the Moon's gradual retreat is stretching our days longer. What single celestial rhythm do you think has most profoundly shaped human civilization? Earth wobbles on its axis with a slow, majestic patience that is almost beyond human comprehension. Picture a spinning top as it begins to lose speed, its handle tracing a slow, lazy circle in the air. Our planet does the very same thing, completing one full wobble every 26,000 years. This grand cycle is known as the precession of the equinoxes. While we live our lives in fleeting years, this celestial clock measures time in civilizations. It was first recorded by the ancient Greek astronomer Hipparchus, who noticed that the stars were not fixed in their positions, but were slowly drifting. This drift is caused by the gravitational pull of the Sun and the Moon on Earth's slightly bulging equator, a relentless tug that makes our planet's axis slowly trace a circle in the cosmos. One of the most tangible effects of precession is the changing of our pole star. Today, Polaris marks the north, but in the time of the ancient Egyptians, the star Thuban was their guide, and in 14,000 years, the brilliant Vega will take its turn. This slow reorientation of the entire sky means that the constellations we associate with our seasons will slowly shift over centuries. But precession is far more than a cosmic light show. It is a fundamental driver of Earth's climate. This wobble changes which hemisphere is tilted toward the Sun during its closest approach to our star. This alternation affects the intensity of the seasons, making northern summers, for instance, milder or more extreme over cycles of thousands of years. This variation in solar energy is a key component of the Milankovitch cycles, the complex orbital rhythms that are believed to trigger the comings and goings of ice ages. A milder summer in the high latitudes might mean that winter snow does not fully melt, allowing ice sheets to gradually build up over millennia. It is humbling to think that the great ice ages were set into motion by this slow, predictable wobble. Ancient cultures, though they lacked our precise instruments, were profoundly aware of this slow dance. Some researchers suggest that monuments like Stonehenge were carefully aligned not just to the Sun, but to this grander celestial cycle, their stones acting as a permanent stone calendar marking a shift that would not be complete for generations. So the next time you look up at the familiar night sky, consider this. The star patterns you see are not permanent. They are a single frame in a film 26,000 years long. How will this gradual shifting of the heavens force us to redesign our calendars in the distant future? And what other long-term climate patterns are already written in this slow, celestial wobble? This first and most ponderous of cosmic clocks sets the stage for timekeepers that operate on far more human timescales. While the precession of the equinoxes is a grand, slow wobble, there is another clock ticking with a faster, more insistent rhythm. Earth's axial tilt is not fixed. It rocks back and forth like a cosmic metronome over a 41,000-year cycle, oscillating between 22.1 and 24.5 degrees. This is the cycle of obliquity, and it is the master dial for the intensity of our seasons. Think of our planet leaning closer to the Sun, then pulling away in a slow, perpetual dance. This small change in angle has monumental consequences. When the tilt is greater, around 24.5 degrees, the hemispheres experience more extreme seasons. Summers become hotter as the pole is angled more directly toward the sun, and winters grow colder as it points away. This is the difference between a mild summer day and a scorching heat wave, but played out over thousands of years. Conversely, when the tilt is minimized, the seasons become much more muted across the globe. This cycle was first rigorously calculated by the Serbian scientist Milutin Milankovic in the early 20th century. He dedicated his life to mapping the complex orbital variations that govern Earth's climate, and the obliquity cycle is a cornerstone of his theory. Climate scientists today point to this 41,000-year rhythm as a direct controller of the great ice ages. How does a slight tilt change, freeze, or thaw a planet? The answer lies in the summer sun. A smaller axial tilt leads to cooler summers, especially in the high latitudes. When summers are too cool, the winter snow does not melt away completely. It persists, reflecting more sunlight back into space, which cools the planet further. Year after year, millennium after millennium, this allows vast ice sheets to accumulate and advance. A greater tilt, with its warmer summers, provides the necessary heat to melt back these glacial frontiers, pushing the planet into an interglacial period like the one we enjoy today. But the influence of this celestial clock extends far beyond the polar ice. It directly shapes the monsoon patterns that billions of people depend on for agriculture. A stronger tilt can intensify seasonal temperature differences, supercharging the atmospheric circulation that drives these vital rains. This rhythmic pulse is even written into the story of life itself, influencing migration patterns and creating environmental pressures that drive evolution. The evidence for this cycle is etched into the deepest ice cores drilled from Antarctica and Greenland. Layer after layer, the ancient ice reveals a clear, repeating 41,000-year signature in the trapped air bubbles and isotopic compositions, a testament to a clockwork universe. So consider this: what if Earth's tilt was frozen at its minimum? Our world would be a place of perpetually gentle, almost non-existent seasons, likely locked in a permanent ice age. Or what if it was stuck at its maximum? We would face wildly swinging extremes of blistering heat and deep cold. The stability of our current climate is a gift of this celestial rhythm, a slow rocking that prevents our world from tipping into permanent chaos. This subtle astronomical change, a mere 2-degree wobble, creates the most dramatic terrestrial consequences, proving that our planet's fate is intimately tied to the sky. Earth's path around the sun is not a perfect circle, but a shape that slowly breathes. Over cycles of 100,000 and 400,000 years, our orbit transforms from nearly round to a more stretched ellipse and back again. This third celestial clock is known as orbital eccentricity, and it acts as a master volume control for the amount of sunlight our planet receives. When the orbit is at its most elliptical, the distance between Earth and the Sun varies dramatically over the course of a single year. At our closest approach, called perihelion, we are millions of miles nearer to the Sun's ferocious energy than we are at our most distant point, known as aphelion. This difference in distance creates a significant swing in the intensity of the seasons. The gravitational dance that drives this change is orchestrated by the giant planets, Jupiter and Saturn. Their immense gravity gently tugs on Earth's orbit, pulling it out of shape in a predictable, rhythmic pattern over vast eons. This celestial clock does not work in isolation. It directly modulates the effects of the other cycles. The climatic impact of our axial wobble, the precession we explored earlier, is either amplified or softened by the shape of our orbit. If a hemisphere is tilted toward the sun at the same time Earth is at its closest approach, that summer becomes profoundly hotter. Conversely, if that tilt coincides with our farthest point from the sun, the summer remains much cooler. It is this powerful combination that is believed to have locked our planet into the great ice age cycles of the last 2.5 million years. For reasons that are still not fully understood, the 100,000-year eccentricity cycle has dominated our recent climate history, its pulse clearly visible in the advance and retreat of continental ice sheets. The evidence for this is not just theoretical, it is physical. Deep beneath the ocean, cores of sediment drilled from the seafloor act as a climate archive. Layer by layer, they preserve the fossilized shells of tiny creatures, and the chemical composition of these shells reveals the ancient temperature and carbon dioxide levels of the ocean. The data tells a stunning story, showing atmospheric carbon dioxide rising and falling in near-perfect sync with the 100,000-year rhythm of Earth's orbital stretch. These celestial clocks were setting the tempo, and the Earth's climate and life were following the beat. So we must ask if our orbit is currently in a phase of low eccentricity, making our seasons relatively mild. What happens as we move into a phase of greater orbital stretch in the distant future? And how do our own human-made changes to the atmosphere interact with these deep, celestial rhythms that have governed our world for millions of years? This cosmic reminder shows that our journey is a dynamic voyage through space, not a static ride. Our sun is a living, breathing heart at the center of our solar system. Its steady beat is not one of light and heat alone, but a powerful magnetic rhythm that pulses through cycles of approximately 11 years. This is the solar cycle, a clock of storm and calm written in fire across the face of our star. We see this cycle in the rise and fall of sunspots, those dark, cooler regions on the solar surface that are actually knots of intense magnetic activity. At the peak of a cycle known as solar maximum, the sun's face becomes freckled with these spots, and it unleashes frequent solar flares and colossal eruptions called coronal mass ejections. These events hurl billions of tons of superheated plasma and radiation out into the solar system, creating the dynamic and sometimes dangerous conditions of space weather. The first detailed records of this cycle come from Galileo Galilei in the 1610s, who risked his eyesight by pointing his telescope at the sun and sketching the moving blemishes he saw. Today, a fleet of advanced solar observatories watches the sun's every move, revealing the churning magnetic dynamo deep within our star that powers this incredible clockwork. When the sun reaches its peak activity, the effects ripple all the way to Earth. The increase in extreme ultraviolet radiation heats and expands our planet's upper atmosphere. This swelling of the air can increase drag on satellites, subtly altering their orbits and threatening the intricate network of technology in low Earth orbit. The intensified solar wind, a stream of charged particles constantly flowing from the sun, can also induce powerful electrical currents in the ground. These geomagnetic storms have the potential to overwhelm power grids, causing widespread blackouts, and can disrupt high-frequency radio communications used by aviation and emergency services. The most famous example of this power was the Carrington event of 1859. A colossal solar superstorm sent currents so strong through telegraph lines that operators received shocks and papers ignited from the sparks. In our modern, hyper-connected world, a similar event today could cause catastrophic damage to our technological infrastructure. Beyond these immediate technological threats, this stellar timepiece may also have a subtle but profound influence on our climate. Periods of exceptionally low solar activity, known as grand minima, have coincided with notably cooler periods on Earth. The most famous of these is the Maunder minimum, a 70-year stretch in the 17th and 18th centuries when sunspots virtually disappeared. This period overlapped with the deepest chill of the Little Ice Age, when frost fairs were held on the frozen River Thames in London. While the sun's direct change in brightness is too small to explain such cooling alone, scientists are investigating a fascinating amplification effect. The reduction in solar ultraviolet radiation during a minimum can alter the chemistry and circulation patterns of our upper atmosphere, potentially creating a cascade of effects that reach the surface and influence global weather patterns. This reveals that the sun's influence is not just a simple matter of turning a dimmer switch, but a complex interaction with the very fabric of our air. We are living in an age of increasing solar activity, with our society more dependent on vulnerable technology than ever before. So we must ask, are we prepared for the next Carrington-level event? How would our daily lives be affected by a prolonged disruption to satellites' power and global communications? The solar cycle is a powerful reminder that our local star is not a constant, placid light, but a dynamic force with its own rhythms that directly shape the environment of our planet. This celestial clock proves that the greatest timekeeper in our sky is the sun itself, and its next heartbeat could change everything. The moon's own orbit holds a secret rhythm, a slow wobble that takes 18.6 years to complete. This is the lunar nodal precession, a celestial clock where the moon's path around Earth does not stay fixed. Instead, the plane of its orbit rotates like a hula hoop slowly twisting around a dancer's waist. As it turns, the points where the moon's path crosses the plane of Earth's equator, called the nodes, gradually shift westward. This subtle change alters the moon's declination, the angle at which it passes overhead relative to the equator. At one extreme of the cycle, the moon rides high in the sky, and at the other, it swings much lower. This shift is not just an astronomical curiosity. It is a powerful force that directly changes the tides that rhythmically wash our shores. When the moon's orbit aligns most closely with the equatorial plane, its gravitational pull works in concert with the sun's to create the most extreme tidal ranges on Earth. The difference between high tide and low tide becomes dramatically wider, flooding and then exposing vast areas of coastline in a rhythmic pulse that has continued for eons. Ancient cultures, with their deep connection to the sea and sky, may have tracked this 18.6-year cycle. Some researchers suggest that the long-term alignments of monuments like Stonehenge could encode not just solar and lunar positions, but this more complex multi-year wobble, serving as a massive stone calendar for a rhythm longer than a single human generation. The modern evidence for this cycle is etched into the tidal gauge records from ports and harbors all over the world. In places like Honolulu and San Francisco, the careful measurements of sea level reveal a clear, repeating 18.6-year signature, a slow heartbeat in the ocean's rise and fall. But the influence of this lunar clock runs far deeper than the shoreline. The enhanced tides during the peak of the cycle churn the coastal seas, driving a powerful mixing of the waters. This mixing brings cold, nutrient-rich water up from the depths, fueling immense blooms of plankton that form the base of the marine food web. This tidal pumping can also influence larger ocean circulation patterns, subtly shifting how heat is distributed across the planet's surface and potentially affecting regional climates. There is even a fascinating and debated link to geology. The immense weight of the extra water during exceptionally high tides may increase pressure on fault lines, with some studies suggesting a statistical correlation between this 18.6-year cycle and the timing of certain earthquakes. The moon's gentle tug is so persistent that it can slightly change the speed of Earth's rotation, minutely altering the length of our day as the tides act as a brake on the spinning planet. This celestial clock highlights a profound truth. The moon is not a passive spectator in the sky. It is an active participant in Earth's environmental systems, governing the pulse of our oceans and perhaps even the stresses deep within our planet. As sea levels rise due to a warming climate, how will this relentless 18.6-year cycle of extreme tides interact with higher baseline water? Will coastal communities face a new era of supercharged flooding during the peak of each lunar nodal cycle? The answers to these questions lie in the continuing dance between our world and its celestial timekeeper. Far beyond the protective bubble of our solar system, a silent rain of atomic shrapnel constantly pours onto our planet. These are galactic cosmic rays, high-energy particles accelerated to nearly the speed of light by distant supernova and other violent events. Their intensity is not constant, but pulses in time with a clock so vast it defies imagination. As our solar system travels on its 240 million-year orbit around the Milky Way, we pass through different galactic neighborhoods, some with higher densities of these penetrating particles than others. This journey creates a cycle of bombardment that may directly sculpt Earth's climate and the very history of life. Our primary defense against this cosmic barrage comes from our own sun. The solar wind, that constant stream of charged particles flowing from the sun, inflates a massive protective bubble called the heliosphere. This magnetic cocoon acts as a shield, deflecting many of the incoming cosmic rays. When the sun is active and the solar wind is strong, the shield is robust. During solar minimums, the shield weakens, and more cosmic rays slip through to reach our atmosphere. This creates a fascinating interplay between the 11-year solar cycle and this much grander galactic rhythm. But what happens when these cosmic rays reach us? The leading hypothesis is both simple and profound. When these high-energy particles strike our atmosphere, they ionize the air, knocking electrons off atoms and creating charged pathways. These pathways can serve as seeds for cloud formation. More cosmic rays could potentially lead to more low-level clouds, which reflect more sunlight back into space and cool the planet. This creates a direct physical link between our position in the galaxy and the temperature of our world. The evidence for this ancient cycle is locked in the ice. Scientists drilling deep into the ice sheets of Antarctica and Greenland have found a historical record written in rare isotopes. When cosmic rays strike our atmosphere, they produce unique forms of elements like beryllium-10 and carbon-14. By measuring the concentrations of these cosmogenic isotopes in ancient ice layers, researchers can reconstruct a timeline of cosmic ray intensity stretching back hundreds of thousands of years. The data reveals clear peaks and troughs, showing times when Earth was subjected to more or less cosmic radiation. Even more startling are the correlations found in the deep time geological record. Some of the great mass extinction events, like the one that ended the Permian period 250 million years ago, appear to have a rough periodicity that aligns with our solar system's passage through the galaxy's spiral arms. These denser regions of stars and gas could provide a much stronger source of cosmic rays. Could a sustained increase in radiation have altered the climate enough to trigger a collapse of the global ecosystem? It is a compelling and haunting possibility that connects the fate of the dinosaurs to the structure of the entire Milky Way. This forces us to confront a humbling scale of time. The 240 million-year galactic year means that since the dinosaurs went extinct, we have completed less than a quarter of a single orbit. Our entire human civilization is a blink in one of these cycles, As we now grapple with the profound climatic changes we are causing ourselves, we must ask a new kind of question. Should our long-term climate models, projections stretching thousands of years into the future, eventually account for our changing address within the galaxy? Will there come a time when humanity, if it still exists, must prepare for a natural shift in the cosmic climate driven not by the sun or our orbit, but by our journey through the starry arms of our galactic home? Deep within the grand wobble of our planet's axis, a much smaller and more intricate dance unfolds. Earth's rotation pole traces a tiny, irregular circle over a period of roughly 14 months, a phenomenon known as the Chandler wobble. It is a free oscillation, a natural shimmy in our planet's spin that subtly changes our orientation in space by just a few meters on the surface. This motion is entirely separate from the vast 26,000-year precession, a faint tremor compared to that slow, majestic nod. The wobble was first identified by the American astronomer Seth Carlo Chandler in 1891, who painstakingly analyzed decades of star positions to prove the pole was not fixed but wandering. Today, a global network of high-precision observatories, from satellite laser ranging to very long baseline interferometry, keeps a constant watch on this subtle motion, tracking its every quiver. The true mystery of the Chandler wobble lies not in its detection, but in its persistence. According to simple theory, this wobble should dampen and vanish within a century due to the internal friction of our planet. Yet it has continued for over a century, its amplitude waxing and waning in an unpredictable pattern. This means something must be constantly exciting it, giving it a fresh push to keep the dance alive. Geophysicists point to a combination of powerful forces as the likely drivers: major shifts in atmospheric pressure across the entire globe, the immense weight of ocean currents sloshing against the seafloor, and even the profound interactions between Earth's liquid outer core and its solid mantle all transfer enough energy to nudge the planet's spin. Data from the International Earth Rotation and Reference Systems Service reveals the wobble's characteristic 433-day periodicity, a clear heartbeat in the precise measurements of the moving pole. Some researchers have even investigated a potential, though highly debated, link to large earthquakes, suggesting that massive tectonic shifts could impart a significant kick to the wobble's amplitude. So we must ask, if this small wobble is constantly being driven by the fluid motions of our air and oceans, does it in turn influence them? The exchange of angular momentum between the solid Earth and its fluid envelopes is a two-way street. These minute variations in rotation could, over many decades, cumulatively affect major climate patterns like the strength of ocean gyres or the paths of jet streams, subtly redistributing heat and moisture around the globe. This terrestrial timepiece, a wobble measured in mere meters, demonstrates that even Earth's seemingly stable spin contains complex, hidden rhythms we are still learning to decipher. What other long-term climatic echoes might be hidden within this 14-month pulse, and what will it tell us about the deep, resonant life of our planet? The planets of our solar system are not drifting in lonely isolation, but are bound together in an intricate gravitational dance. Their orbits are linked by mathematical harmonies, subtle rhythms where one world completes a certain number of loops around the sun. In the same time, another world completes a different number. These are planetary orbital resonances, a cosmic clock built from synchronized orbits. When two planets fall into a resonance, their gravitational tugs on each other begin to repeat in a predictable pattern, like two pendulums swinging in perfect offset time. This creates a stable, repeating rhythm that can persist for hundreds of millions of years, subtly guiding the long-term architecture of our entire solar system. One of the most significant is the 5:2 resonance between Jupiter and Saturn. For every 5 orbits Jupiter makes around the Sun, Saturn completes almost exactly 2. This grand gravitational partnership is a primary regulator of the solar system's stability, its rhythmic pull helping to shepherd the orbits of the other planets and countless smaller bodies. But these harmonies are not just a background hum, they can directly influence Earth over geological timescales. The combined gravitational pull from the giant planets, locked in their resonant patterns, can gently nudge Earth's own orbit, minutely altering its eccentricity or its orientation in space. These tiny changes, amplified over millions of years, feed directly into the Milankovitch cycles, becoming another hand on the celestial clock that governs the coming and going of ice ages. The influence of resonance extends into the asteroid belt, a vast collection of rocky debris between Mars and Jupiter. Jupiter's immense gravity creates regions of stability and chaos within the belt through powerful resonances. Asteroids that are captured by these gravitational harmonies have their orbits stretched and pulled, eventually being flung inward toward the Sun, crossing Earth's path. Some of the great impact events in our planet's history may have been timed by these celestial rhythms, as a resonance cleared out a swarm of asteroids and sent them on a collision course with our world. There is even a fascinating, though still debated, hypothesis that the gravitational pull of the planets, as they align in their resonant cycles, can exert a tiny tidal force on the Sun itself, perhaps influencing the dynamo that drives the solar cycle and its sunspots. The evidence for the power of these resonances is written in the early history of our solar system. Planetary scientists believe the giant planets migrated from their original orbits in the solar system's youth. As they moved, they crossed powerful resonances with each other, a gravitational upheaval that likely scattered the primordial asteroid and comet population, triggering a violent period of bombardment known as the Late Heavy Bombardment that pummeled the inner planets. This reveals that these mathematical harmonies are not just about maintaining order, they can also be agents of profound change. So we must wonder, did a planetary resonance indirectly orchestrate one of Earth's great mass extinctions by guiding a killer asteroid to our door? And as we discover more planetary systems around other stars, will we find similar gravitational symphonies, or is the precise tune of our own solar system a unique composition that made our stable, life-bearing world possible? This cosmic clock reveals the hidden mathematical music that keeps the planets in time, a silent rhythm that has guided Earth's deepest history. Our planet's magnetic field is a shield of invisible force, a bubble of protection generated by the churning of molten iron in Earth's outer core. Yet this guardian is not constant. It has a startling habit of turning itself inside out. Earth's magnetic north and south poles have swapped places hundreds of times, a chaotic and irregular clock that ticks over an average of 300,000 years. These geomagnetic reversals are one of the most dramatic resets in our planet's deep history. The evidence for this is locked in stone. When volcanic lava cools, tiny magnetic minerals within the rock freeze in place, aligning themselves with the direction of the planet's magnetic field at that exact moment. By reading this fossilized compass in ancient rock layers around the world, paleomagnetists have pieced together a timeline of these flips, a natural chronology written in the Earth itself. The process of a reversal is not a sudden switch. It begins with a long, slow decline in the magnetic field's strength, a weakening that can last for thousands of years. During this extended twilight, our protective shield could drop to as little as 10% of its normal power. This is when the cosmic consequences begin. A weakened magnetic field allows more of the Sun's radiation and powerful galactic cosmic rays to penetrate deeper into our atmosphere. The potential biological effects are profound. Could an increase in radiation have driven mutations, accelerating evolution in some species while dooming others? Some scientists have found correlations between past extinction events and periods of geomagnetic instability, suggesting that this deep Earth clock may have directly influenced the story of life. The most stunning visual proof of these reversals is found not on land but on the seafloor. As magma erupts along mid-ocean ridges and cools to form new crust, it records the magnetic field's polarity like a continuous tape recorder. The result is a stunning zebra stripe pattern of magnetic bands parallel to the ridge, with each stripe representing a period of normal or reversed polarity. It was this very pattern that provided the definitive evidence for the theory of plate tectonics, proving that the seafloor was spreading and the continents were adrift. The timing of these reversals is wildly irregular, governed by the turbulent, unpredictable dynamo of Earth's liquid outer core. Supercomputer models simulate this vast, swirling ocean of molten metal, revealing how complex interactions can cause the magnetic field to weaken, twist, and eventually collapse before reorganizing itself with the poles reversed. Our current field strength has been decreasing for the last 2,000 years, leading many to ask a pressing question: are we on the precipice of the next great reversal? For ancient life, a flip may have been a slow-motion environmental stressor. For our modern world, it is a technological nightmare. A weakened magnetic field would leave our power grids, satellite networks, and global communications incredibly vulnerable to solar storms and cosmic radiation. A single powerful solar flare during a period of magnetic weakness could cripple civilization. This celestial clock reminds us that our safety is not guaranteed by a permanent shield, but is maintained by the restless, unpredictable heart of our own planet, a dynamic force whose next heartbeat could change the very nature of our world. Ancient skywatchers discovered a rhythm in the heavens so precise it could predict the future. This is the Saros cycle, a celestial timekeeper of 18 years, 11 days, and 8 hours that orchestrates the grand spectacle of eclipses. Picture 3 celestial bodies falling into a near-perfect alignment, with the Sun, Earth, and Moon returning to almost the exact same geometric configuration they held nearly 2 decades prior. When this happens, a solar or lunar eclipse with remarkably similar characteristics will occur once again. The brilliant astronomers of ancient Babylon were among the first to formally document this pattern, using its unwavering regularity to forecast the terrifying moments when the sun or moon would seemingly vanish from the sky. This was not a discovery made in one culture alone. Historians of astronomy note that the Maya and the ancient Chinese also independently unlocked this secret, proving that humanity's quest to understand celestial order is a universal story. The mathematical heart of the Saros is stunningly elegant. The cycle equals exactly 223 synodic months, the time from one new moon to the next. This is also nearly identical to 242 draconic months, the time it takes the moon to return to the same node where its path crosses the ecliptic. This dual alignment is the key, ensuring the moon is both at the correct phase and at the correct orbital intersection to cast its shadow upon the Earth or fall into Earth's own shadow. But an eclipse series is a living thing that migrates. Each subsequent eclipse in a Saros family occurs about 120 degrees westward on the globe, tracing a path across the planet over a lifetime that can span between 1,226 and 1,550 years. A series is born with a faint partial eclipse near the poles, grows to maturity with stunning total eclipses across the tropics, and eventually fades away at the opposite pole. This explains why not every eclipse is part of a Saros series. The geometry must be precise enough to repeat, and each series has a finite beginning and end. The power of this cycle extends from ancient prophecy to modern physics. One of the most famous pairs linked by the Saros is the solar eclipse of 1919 and its successor in 1999. The first provided the crucial observations that confirmed Einstein's theory of general relativity by showing starlight bending around the Sun, while the latter offered a spectacular display of totality over Europe, witnessed by millions. This celestial clock has even become a tool for historians, allowing them to pinpoint the exact dates of ancient battles or royal coronations mentioned in texts that describe an eclipse. How did cultures without telescopes or advanced mathematics achieve such a deep understanding of a cycle that spans generations? Their legacy was built on millennia of patient, meticulous observation, with knowledge passed down through countless lifetimes. What other intricate celestial patterns might we be missing today, simply because we lack their generational patience? The Saros cycle stands as a testament to humanity's enduring partnership with the cosmos, a lunar solar clock that has guided our curiosity for thousands of years. This grand wobble of our axis traces a circle not just in space, but through human history itself. The precession of the equinoxes completes one full rotation every 25,800 years, a span so vast that ancient astronomers saw it as a single great year. This is the slowest celestial clock that still operates on a scale we can almost comprehend, a backdrop against which entire civilizations are born, flourish, and fade. The vernal equinox, the point in the sky where the sun crosses the celestial equator each spring, does not hold its position. It drifts westward, spending roughly 2,150 years passing through each of the 12 constellations of the zodiac. This slow precession gave rise to the concept of astrological ages, where each era is named for the zodiacal constellation that hosted the dawn sun on the spring equinox. For the last 2 millennia, we have been living in the age of Pisces, but we are now on the cusp of the much-discussed age of Aquarius. This is not a sudden event, but a gradual transition that takes centuries, a slow turning of a cosmic page. The Babylonians, meticulous sky watchers who first codified the zodiac over 2,500 years ago, were among the first to grasp the immense scale of this cycle. They wove it into their cosmology, viewing the great year as a cycle of creation and destruction for the world. This idea resonated across cultures, from the Hindu concept of the Yuga cycle to the Greek philosopher Plato's notion of a perfect year that brought the cosmos back to its starting point. This cultural timepiece connects raw astronomical reality to the deepest human longings for order and meaning in the cosmos. The astronomical basis is pure physics, the same gravitational tugging that drives the precession. But the human interpretation is a story written in stone and myth. The Great Pyramid of Giza, for instance, was constructed around 4,500 years ago. At that time, the North Celestial Pole was not marked by our Polaris, but was located in a dark region of the sky near the star Thuban. The pyramid's southern shaft was aligned with the star Alnilam in Orion's belt, while its northern shaft pointed directly to the pole star of its age. This was not just symbolic, it was a perfect alignment with the celestial clock of its era, a frozen moment in the great year. The precise length of this cycle is not a fixed number. It varies slightly due to the subtle gravitational nudges from the other planets, a phenomenon called planetary precession. This is why you might see the great year's duration listed as 25,771 years or 25,800, a tiny difference over such a vast span, but a reminder of the dynamic complexity of our solar system. So we must ask, if the great year is a clock that measures the lifespan of civilizations, what does it mean that our modern world has arisen in the final moments of the Piscean age? How did this slowest of celestial rhythms shape the development of ancient calendars, which tried to reconcile the lunar month, the solar year, and this grander cycle of the stars? This cultural timepiece reminds us that our view of the cosmos is never just about physics. It is a story we tell ourselves, written in the slow, patient turning of the heavens. The moon is slowly stealing our days. It pulls on our oceans, and that gentle, persistent tug acts as a brake on our planet's spin, transferring Earth's rotational energy outward to push the moon itself into a higher orbit. Each year, our celestial companion drifts about 3.8 centimeters farther away, a gradual retreat that has been unfolding for over 4 billion years. This process, known as tidal acceleration, is a fundamental clock that is literally changing the length of our day and the distance to our moon. Planetary scientists explain this as a cosmic exchange of energy. The Earth's rotation drags its oceanic tidal bulges slightly ahead of the direct line to the moon. The gravity from these off-center bulges then pulls the moon forward in its orbit, giving it a tiny boost that pushes it further away, all while the moon's gravity pulls back on the bulges, slowing our spin down. The rate of this change is not constant. It depends entirely on the shape of our planet's oceans. When the continents are arranged in a way that creates vast, unobstructed basins, the tides can slosh more freely, creating greater friction and a faster transfer of energy. In eras when the continents block these flows, the process slows. We can read the history of this celestial clock not in the stars, but in the fossils of ancient sea creatures. Corals and mollusks laid down microscopic growth lines, a daily and annual diary in stone. By counting these lines in fossils from the distant past, geophysicists have made a stunning discovery. Precambrian stromatolites dating back 900 million years reveal that an Earth year then contained over 480 days, each one lasting only about 18 hours. The lunar month was also shorter, with the moon orbiting closer and faster in a younger, more dynamic system. A faster spinning Earth would have created a profoundly different world. The Coriolis force driving weather patterns would have been stronger, likely generating more intense and frequent storms. The sun would have raced across the sky, and the closer moon would have loomed larger, its gravitational pull creating far more extreme tides that crashed over the continents. How would life have adapted to such a rapid cycle of light and dark? Would complex organisms have evolved the same rhythms on an 18-hour clock? This process will not continue forever. Billions of years from now, the Earth's rotation will have slowed to match the moon's orbital period, locking the two in a synchronous embrace. One side of the Earth will permanently face the moon, just as one side of the moon always faces us now. The lunar month and the Earth day will be the same length, stretching to about 47 of our current days. This celestial dance will finally cease, the energy transfer complete. Tidal acceleration is a clock that measures the evolution of a relationship, a slow motion parting that has shaped our past and will ultimately define our distant future. What other gradual changes, almost imperceptible in a human lifetime, are quietly reshaping the cosmic environment we call home? Our solar system rides a galactic wave. Every 64 million years, our entire planetary neighborhood completes a single bob up and down through the dense central plane of the Milky Way. This vertical oscillation is a grand roller coaster ride on a scale almost impossible to grasp, carrying us from the crowded galactic disk out into the sparse halo and back again. This motion is driven by the gravitational pull of the galaxy's mass, not just from the bright stars we see, but from the vast, unseen reservoir of dark matter that permeates everything. As the Sun and its planets travel on this path, we pass through environments of wildly different character. When we are high above or below the galactic plane, we sail through a relative void. But when we plunge through the plane itself, we encounter a thick soup of interstellar gas and dust, and the gravitational influence of vast, dark molecular clouds. Galactic astronomers map this journey, while paleontologists uncover its potential echoes in the story of life. The heliosphere, that protective magnetic bubble blown by the solar wind, is our first line of defense. During our passage through a dense interstellar cloud, this bubble can be compressed, shrinking the zone of protection around our planet. A smaller heliosphere would allow more powerful galactic cosmic rays to penetrate into the inner solar system, bathing Earth in higher levels of radiation. What could this mean for life? One compelling hypothesis suggests this increased radiation could lead to higher mutation rates in DNA, potentially accelerating evolution, but also increasing the risk of cancer and genetic damage for large creatures. It could also influence cloud formation and climate, adding a deep space stressor to our planet's environment. The most tantalizing evidence comes from the fossil record itself. Detailed statistical analyses of marine biodiversity over the last 500 million years reveal a mysterious rhythm. The diversity of life in the oceans appears to rise and fall with a rough period of about 62 million years, a pulse that aligns eerily well with our solar system's vertical oscillation. It is as if the history of life on Earth has a hidden metronome, ticking in time with our journey through the galaxy. These biodiversity dips are not always mass extinctions, but they are times when the rate of species formation seems to slow and the rate of extinction subtly increases. Could our passage through a galactic zone of intense cosmic radiation be the cause? The exact period is difficult to pin down with perfect precision because the fossil record is incomplete and the galaxy's gravitational field is complex, but the correlation is a profound puzzle. This forces us to consider a humbling possibility. Did humanity's own rise to prominence occur during a particularly calm and stable phase of this 64 million-year cycle? Are we the beneficiaries of a fortunate galactic address, sailing for now in a clear and quiet stretch of space? Our entire recorded history is less than an instant in this clock's measure, a single note in a symphony that plays out over geologic eras. What will happen to life on Earth or to any civilization that endures when we next dive through the crowded and dangerous heart of the galactic plane? This vertical oscillation reminds us that our fate is tied not just to the Sun or the Moon, but to the structure of the galaxy itself. Mercury's elliptical path around the Sun is itself a slowly spinning clock. Its entire orbit rotates, causing the point of its closest approach to the Sun, called perihelion, to gradually shift forward in space. This is the apsidal precession of Mercury, a celestial dance that takes 225,000 years to complete just one full cycle. The primary force nudging its orbit is the collective gravity of the other planets, especially Venus and Jupiter, which constantly tug on Mercury, distorting its elliptical path over millennia. But in the 19th century, astronomers like Urbain Le Verrier noticed a problem. Even after they meticulously calculated every planetary perturbation, Mercury's perihelion was advancing slightly faster than Newton's laws of gravity could explain. The discrepancy was tiny, just 43 arcseconds per century, a shift so small it would take over 3 million years for the perihelion to advance the width of a full moon in the sky. Yet it was undeniable, a stubborn flaw in the otherwise perfect clockwork of Newtonian physics. This tiny anomaly became a ghost in the machine of the solar system, a mystery that would wait half a century for its solution. The answer arrived with a revolution. Albert Einstein, developing his general theory of relativity, used Mercury's orbit as a key test. His theory proposed that gravity is not a mysterious force, but the curvature of spacetime caused by mass. The Sun, as a massive object, warps the fabric of the universe around it. Mercury, being the closest planet, orbits through this most severely curved region of spacetime. As it travels, the planet follows the curved geometry, causing its orbital path to gradually rotate in a way that Newtonian physics could not account for. The calculated relativistic effect perfectly matched the observed 43 arcseconds, providing one of the first and most powerful confirmations that Einstein's radical new description of gravity was correct. Why does Mercury show this effect so much more clearly than, say, Earth or Mars? It is a matter of speed and proximity. Mercury moves fastest when it is nearest the Sun, deep within its gravity well where spacetime curvature is most extreme. This combination of high velocity and strong curvature maximizes the relativistic effects on its orbit. While all planets experience this, the signal is strongest for the innermost world, making Mercury a unique laboratory for fundamental physics. Today, planetary dynamicists continue to track the orbits of planets with incredible precision using radar and spacecraft. Each new measurement of Mercury's slow waltz further constrains our models of gravity, testing whether Einstein's theory holds perfectly or if there are even more subtle deviations waiting to be discovered. Could future observations reveal a crack in the foundation of general relativity, pointing the way to a deeper, more complete theory of the universe? This planetary clock, operating on a timescale far beyond human history, reminds us that the laws of physics themselves are written in the motion of the heavens, and that the smallest anomaly can unravel our entire understanding of reality. A laser beam fired from Earth takes a one-way trip to the Moon and back. This is not science fiction, but the core of the most precise celestial clock humanity has ever built. Since 1969, when the Apollo 11 astronauts placed the first retroreflector array on the lunar surface, scientists have been firing pulses of light at these mirrored corner cubes. By timing the light's round trip with exquisite accuracy, they measure the instantaneous distance to the Moon down to the millimeter. This ongoing experiment, the Lunar Laser Ranging Project, transforms a simple principle into a profound tool for cosmic discovery. The retroreflectors work like perfect passive ping-pong balls, sending any incoming light pulse directly back to its source regardless of the angle it arrives from. Ground stations like the powerful facility at the Apache Point Observatory fire a short, focused laser pulse toward the Moon. A telescope there then patiently waits to catch the handful of photons that make the nearly 500,000-mile journey back. The timing of that return, about 2.5 seconds later, reveals the exact distance at that instant. Repeating this over decades paints a stunningly detailed picture of the Moon's slow retreat from Earth. We now know the Moon is drifting away at about 3.8 centimeters per year, but the laser data shows this rate is not perfectly constant. It fluctuates slightly with the changing shape of Earth's ocean basins, the sloshing of our tides, and even the slow rebound of our planet's crust after the last ice age. These complex tidal interactions are written into the laser timeline with millimeter precision. The implications reach far beyond lunar motion. This data is a direct record of Earth's changing spin. By tracking the Moon's position as a fixed reference point, scientists can detect minuscule variations in the length of our day caused by the sloshing of Earth's liquid core, the transfer of angular momentum from the atmosphere, and the gravitational pull of the Sun. The laser range acts as a galactic stopwatch for our planet's rotation. It even tests the bedrock of physics itself. The data provides the most stringent limits on the stability of the gravitational constant, Big G. Is the force of gravity truly unchanging over cosmic time, or does it drift by an infinitesimal amount? So far, the laser echoes from the Moon confirm that gravity has not changed by more than 1 part in 100 billion per year. The precise orbital path of the Moon also serves as a test for Einstein's theory of general relativity, with the measurements matching its predictions perfectly. There is even a fascinating bonus hidden in the data. The way the Moon wobbles on its axis as it orbits Earth suggests it is not a completely solid ball. The laser-ranging measurements provide strong evidence for a liquid core, a sloshing ocean of molten rock deep within our celestial companion. What began as a flag-planting mission has become a multi-generational experiment, a technological timepiece that turns light into a ruler for the cosmos. What other secrets will we unlock as we continue to ping the Moon with light for another 50 years? Could we one day detect the subtle ripples of passing gravitational waves by watching the Moon's distance jiggle? This human-made clock proves that by reaching for the Moon, we did not just explore another world, we gained a new lens to understand our own. The gentle pull of our galaxy is a force you cannot feel, yet it tugs on our entire solar system from 50,000 light-years away. This is the galactic tide, a subtle but relentless stretching force born from the Milky Way's immense gravitational field. Just as the Moon's gravity raises tides in our oceans, the galaxy's gravity creates a tide in the vast cloud of comets that surrounds us. Far beyond the orbit of Pluto, in the deepest freeze of space, lies the Oort cloud. It is a spherical shell of icy bodies, a trillion potential comets orbiting at the very edge of the Sun's gravitational grasp. The galactic tide is weak, but over millions of years its persistent pull can nudge these dormant icebergs, slightly altering their paths until they fall inward on a long journey toward the inner solar system. Dynamicists who map the orbits of these small bodies see the galaxy as a grand clockmaker. As our solar system rides its 64-million-year roller coaster, bobbing up and down through the galactic plane, the strength of this tide changes dramatically. When we are farthest from the crowded plane, sailing in the sparse galactic halo, the tidal force is at its strongest. The Sun's gravitational hold on these outermost comets is weakest here, making them most vulnerable to the galaxy's gentle push. This rhythmic variation in the tide's strength may act as a metronome for comet showers, potentially turning up the flux of incoming bodies every 30 to 35 million years. The evidence for this celestial timing is written in the scars on our own planet. Statistical analyses of Earth's impact craters reveal a tantalizing pattern. The ages of large craters are not randomly distributed. They seem to cluster with a rough periodicity that aligns with this galactic rhythm. It is as if the galaxy itself has been tapping a slow beat, and every so often, that beat dislodges a snowball from the edge of darkness and sends it on a collision course with our world. How does this galactic tide compare to another cosmic trigger, the occasional close passage of a star? While a stellar flyby can cause a sudden and dramatic shakeup in the Oort cloud, the galactic tide is the constant background hum, a perpetual drizzle of cometary perturbations that provides a steady supply of new visitors to the inner solar system. The two mechanisms might even work together, with a stellar passage stirring the cloud and the tide then efficiently guiding the disturbed comet sunward. So we are left with a profound and unsettling question. Given our current position in the galactic oscillation, are we in a period of heightened impact risk or relative safety? Our solar system is currently moving away from the galactic plane, a phase where the tide is strengthening. Does this mean the cosmic clock is ticking toward a more perilous time? A future where the sky may once again rain down frozen remnants from the birth of our solar system. This celestial clock connects the most distant reaches of our galaxy to the very safety of our planet, a reminder that the gravity of 100 billion stars is quietly orchestrating events in our own backyard. Deep within the planet's churning heart, a second, more secret wobble takes place. Earth's free core nutation is a small, irregular sway in our rotation with a period of about 430 days, a whisper of motion generated by the interplay between the solid mantle and the liquid outer core. This is not the Chandler wobble, which is a motion of the entire planet's spin axis. Instead, this is a signal from the deepest interior, a sloshing of the fluid core inside its rocky shell. The motion arises from a subtle misalignment. The rotation axis of the solid mantle and the rotation axis of the liquid core are not perfectly aligned. This offset causes the fluid core to press against the mantle's container, exerting tiny torques that make the whole system wobble in this distinct 430-day rhythm. It is a normal mode of our planet's rotation, a natural resonance that was predicted by theory long before our instruments were sensitive enough to detect its faint signature. The detection came from the most precise astronomical tools we have, very long baseline interferometry, which uses networks of radio telescopes across the globe to measure Earth's orientation in space with breathtaking accuracy. The data from these observations clearly shows the 430-day period imprinted on the Earth orientation parameters, a ghostly fingerprint of the fluid core's motion. This deep Earth clock does more than just wobble, it subtly influences the speed of our planet's spin. The exchange of angular momentum between the sloshing core and the solid mantle causes tiny, sub-decadal variations in the length of our day. These changes are minuscule, measured in milliseconds, but they are a direct consequence of this internal dance. The unpredictable variations in the wobble's amplitude and phase are themselves a crucial data stream. They reveal the physical properties at the core mantle boundary, a region of immense heat and pressure where the solid rock of the mantle meets the swirling iron ocean of the outer core. The way the wobble changes tells geophysicists about the viscosity of the fluid, the topography of the boundary, and the strength of the magnetic coupling between the two layers. This leads to a fascinating and unresolved question. How does this subtle 430-day pulse interact with other sudden events deep within the Earth, like the geomagnetic jerks that cause abrupt shifts in our magnetic field? Could the same turbulent dynamics in the core that generate these jerks also be giving the free core nutation an occasional, unpredictable kick? This hidden rhythm demonstrates that our planet's rotation is a symphony of overlapping clocks, each with its own origin and its own story to tell about the hidden world beneath our feet. The Sun is not a stationary king on a cosmic throne. It is a dancer pulled by its own courtiers in a slow, graceful waltz. The center of our solar system is not the Sun itself, but a point called the barycenter, the system's balancing point of mass. This center of mass is constantly shifting as the giant planets, especially Jupiter and Saturn, move in their vast orbits. The Sun, in response, makes small loops and circles around this moving point, a motion known as the solar inertial motion. The dominant rhythm of this dance is a cycle of about 178.7 years. During this time, the Sun can sometimes be found far outside the barycenter, pulled off-center by the combined gravity of the gas giants. This elegant orbital choreography is an undeniable fact of celestial mechanics, but it leads to a profound and controversial question. Could this planetary dance actually influence the Sun's turbulent magnetic heart? Some heliophysicists point to intriguing correlations. When the Sun's motion around the barycenter is most irregular and loopy, its path seems to coincide with periods of suppressed solar activity. The historical record of sunspots stretching back centuries shows hints of a rhythm that echoes this 179-year cycle. The hypothesis is that the planets exert a tiny tidal force on the Sun, much like the Moon pulls on our oceans. This force is far too weak to create a physical bulge on the solar surface. but it might be just enough to subtly influence the flow of plasma in the Sun's outer convective zone. This could, in theory, affect the solar dynamo, the engine that generates its magnetic field and produces sunspots. The debate is fierce. Critics argue that the gravitational influence of the planets is minuscule, a mere whisper against the roaring nuclear furnace and complex magnetohydrodynamics of the Sun. They see the correlations as coincidental, not causal, pointing out that the energy required to drive the solar cycle must come from within the star itself. Yet the tantalizing patterns persist, suggesting that the giant planets might be acting as a metronome, setting a slow background tempo to which the Sun's own internal rhythms sometimes synchronize. Could future space-based solar observatories, with their exquisitely detailed views of our star's interior, finally gather the evidence needed to settle this centuries-old debate? This celestial clock presents a humbling possibility that the planets we orbit may, in a subtle and indirect way, help conduct the symphony of their parent star. Earth's rotation is never perfectly steady. Our planet's spin fluctuates by tiny amounts, speeding up and slowing down in a complex rhythm governed by the restless motion of its air, water, and even its molten core. These length-of-day variations, measured in mere milliseconds, form a geophysical clock that reveals our world as a dynamic system of interconnected parts. Primary cause is a constant exchange of angular momentum between the solid Earth and its fluid envelopes. Think of a spinning ice skater. When she pulls her arms in, she spins faster. When she extends them, she slows. Earth experiences a similar effect on a planetary scale. Powerful winter winds rushing from west to east can act like those pulled-in arms, transferring angular momentum to the solid planet and minutely speeding up its rotation. Vast ocean currents sloshing against continental shelves do the same, while deep inside, the sloshing of the liquid iron core against the mantle exerts its own subtle torque. Geodesists track these changes with astonishing precision by comparing the planet's rotation, measured against distant quasars, with the unerring tick of international atomic time. The data reveals clear patterns. There is a seasonal cycle where the length of day typically shortens in the northern hemisphere winter and lengthens in the summer, following the intensity of the atmospheric circulation. Then there are slower, decadal wobbles linked to the turbulent dynamics at the core mantle boundary, a region of such immense heat and pressure that it governs changes in rotation over years and decades. Even singular, violent events leave their mark. A major earthquake that redistributes massive amounts of rock, like the 2004 Sumatra event, can suddenly change the planet's rotation and shave a tiny fraction of a second off the day. This is why we occasionally need to add a leap second to our official clocks, a human acknowledgement that the cosmic clock of Earth's spin is ultimately in charge. So we must ask, if these millisecond changes accumulate over millions of years, how have they subtly altered the trajectory of life's evolution? And how do these tiny rotational shifts interact with the climate system, perhaps even influencing the very ocean currents and wind patterns that cause them? This celestial clock proves that our planet's most fundamental rhythm is a conversation between its rock, its water, its air, and its fire. Our entire solar system is racing through the cosmos at a breathtaking speed of 370 kilometers per second. This is not a relative speed compared to a nearby star, but our absolute velocity against the most fundamental backdrop in existence, the afterglow of the Big Bang itself. This relic radiation, known as the cosmic microwave background, fills every cubic centimeter of space with a faint, cold whisper of light. As we move at this incredible clip toward the constellation Leo, we plow through this sea of photons, and our motion imprints a subtle fingerprint upon it, a phenomenon called the dipole anisotropy. The effect is a direct result of the Doppler shift, the same principle that makes a siren's pitch change as it speeds past you. The radiation in the direction we are heading appears very slightly compressed and therefore warmer, while the radiation behind us is stretched and appears cooler. The difference is minuscule, only a few thousandths of a degree, but it is unmistakable. This cosmic dipole was first conclusively mapped by the Cosmic Background Explorer satellite, COBE, in the early 1990s. Its data revealed this fundamental lopsidedness in the universe's oldest light, providing a fixed coordinate system for our motion. Later missions, the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have refined this measurement to exquisite precision. The Cosmic Microwave Background Dipole is our ultimate speedometer, a universal clock that measures our drift through the fabric of space-time. This absolute reference frame allows cosmologists to disentangle our local motion from the larger cosmic flows. We can now precisely calculate how the Sun and its planets are moving relative to our local group of galaxies, and even measure the gravitational pull from immense nearby structures like the Great Attractor, a mysterious concentration of mass in the direction of the Centaurus constellation. Why does this matter? For the first time in history, we have a true north on a cosmic scale. Every other measurement of motion, from a car on a highway to a star orbiting the galactic center, is relative to something else. The cosmic microwave background provides the one stationary background against which all other movements can be gauged. It is the still point in the turning universe, a fundamental rest frame woven into the geometry of reality. This celestial clock situates our local journey within the grandest possible context. We are not just orbiting the galaxy, we are being swept along by vast gravitational tides in an ocean of dark matter and dark energy. What larger, slower currents might we discover as our instruments become even more sensitive? Will we one day map the full flow of our galactic neighborhood through the cosmos, tracing our path back to the very origins of the great cosmic web? This universal timepiece reminds us that even at rest on Earth, we are all passengers on a spacecraft hurtling through the primordial light of creation. Our own air breathes in a slow, celestial rhythm. The entire atmosphere rises and falls in a daily pulse, pushed by the sun's heat and pulled by the gravity of the sun and moon. These are the atmospheric tides, a hidden clockwork in the sky that governs pressure patterns across the globe with the precision of a metronome. While you cannot see or feel this motion directly, sensitive barometers have recorded its steady beat for centuries. The dominant force is thermal. The sun heating the atmosphere each day causes it to expand, creating a powerful 24-hour pressure wave that travels around the world. Superimposed on this is a 12-hour harmonic, a smaller pulse that makes pressure typically peak around 10 in the morning and 10 at night, a pattern first noted in barometric logs from the 1700s. The moon adds its own subtle signature, a gravitational pull that creates much weaker 12.4-hour and 24.8-hour oscillations in the air itself. This complex interplay creates a global symphony of pressure changes that directly shapes our weather. The rising and falling air influences cloud formation and can modulate rainfall patterns, especially in the tropics where these tides interact with daily thunderstorm cycles. The effects reach all the way to the edge of space. In the ionosphere, the atmospheric tide causes electron densities to wax and wane, disrupting radio communications in a predictable daily cycle. The constant motion of this massive body of air also exerts a frictional force on the planet itself. By transferring angular momentum, atmospheric tides act as a brake on Earth's rotation, contributing to those millisecond variations in the length of our day. This aerial clock even touches our technology in orbit. The tidal expansion and contraction of the upper atmosphere changes its density, directly affecting the drag experienced by satellites and subtly altering their paths through space. Data from the global network of weather stations shows this clearly, with barometric pressure charts from places like the tropical Pacific revealing the unmistakable, repeating peaks and troughs of this celestial pulse. So we must ask, as human activity warms the planet, how will climate change alter this ancient rhythm? Will a hotter atmosphere breathe faster or slower? And how will that shift the wind patterns and rainfall billions depend on? This celestial clock reminds us that the sky above is not a passive void, but a fluid, ticking heart, driven by the same cosmic forces that move the seas. Our solar system weaves through the galaxy's grand spiral arms in a rhythm that spans ages. Roughly every 150 million years, our Sun and its planets cross one of these dense, star-filled regions, a journey that fundamentally alters our cosmic environment. Within these spiral arms, the stellar density is far higher, the rate of stellar explosions increases, and vast, dark molecular clouds drift like celestial icebergs. This periodic passage is a galactic clock of immense power, one that may have left its signature in the very rock and life of our world. The mechanism is a dance of differential speeds. The spiral arms themselves are not fixed structures of stars, but density waves, patterns of compression that move through the galactic disk at their own stately pace. Our solar system, orbiting the galactic center independently, periodically overtakes these waves or is overtaken by them, like a car moving through a slow-moving traffic jam. Each crossing plunges us into a more crowded and violent neighborhood. Galactic astronomers point to the potential consequences. An increased rate of nearby supernova could bathe Earth in intense radiation. The gravitational pull from the higher density of stars and gas might perturb the distant Oort cloud, sending a shower of comets toward the inner solar system. The interstellar medium itself becomes denser, potentially compressing the protective bubble of the heliosphere and allowing more galactic cosmic rays to reach our planet. Paleoclimatologists and geologists search for the echoes of this clock in Earth's deep past. Intriguingly, the ages of large impact craters on our planet show a possible periodicity of about 140 million years. Could this be the timer of spiral arm crossings, triggering epochs of bombardment? Analyses of marine fossil diversity also reveal a mysterious rhythm, with biodiversity dipping and rising on a similar timescale. Some of the great mass extinctions, while not perfectly aligned, cluster near these potential crossing times, suggesting the galaxy itself may have been a silent partner in the remaking of life on Earth. The changing interstellar environment could influence climate directly. A compressed heliosphere and heightened cosmic ray flux might seed more clouds, cooling the planet and perhaps contributing to the onset of ice age epochs. The evidence is not yet conclusive, but the pattern is a compelling puzzle that connects the largest scales of the galaxy to the smallest details in the fossil record. So we must ask, where are we now in this grand cycle? Current data suggests our solar system is located in a relatively sparse region between arms, a local bubble that may have offered a stable environment for millions of years. But the clock is still ticking. As we continue our quarter-billion-year orbit, our path is destined to carry us back into the turbulent spiral arms. What will that next crossing mean for the future of Earth's climate and the life it holds? This celestial clock binds our planet's destiny to the architecture of the entire Milky Way. The ground beneath your feet is still ringing from a blow struck half a century ago. Our entire planet vibrates like a giant bell after a major earthquake, humming with resonant frequencies that can last for days or even weeks. These are Earth's rotational normal modes, the fundamental tones of our world, and they form a seismic clock that reveals secrets from the core outward. Each vibration has a characteristic period, from a few minutes to several hours, creating a natural timekeeping system that measures the physical properties of the planet itself. The first clear detection of these free oscillations came after the Great Chilean Earthquake of 1960. For the first time, a network of newly installed sensitive seismometers recorded not just the sharp jolts of the initial quake, but the persistent, low-frequency hum of the entire globe resonating. It was as if scientists had finally learned to listen to the Earth's own voice. When a massive earthquake occurs, it acts like a giant mallet striking the planetary bell. The energy released is so immense that it sets the entire Earth vibrating in a complex set of patterns. Some vibrations, called spheroidal modes, involve the planet alternately compressing and expanding, while others, known as toroidal modes, involve twisting and shearing motions. Each of these distinct modes is sensitive to different depth ranges within the planet, from the brittle crust down to the solid inner core. The specific frequencies of these vibrations are controlled by the density and elasticity of the material they pass through. By meticulously measuring these frequencies, geophysicists can create a detailed picture of Earth's interior, much like a doctor uses an ultrasound to see inside a human body. The Sumatran earthquake of 2004 was so powerful that it excited hundreds of these normal modes simultaneously. Data from the Global Seismometer Network recorded a stunning symphony of planetary vibrations, providing an unprecedented snapshot of our planet's deep structure. Why are certain modes more strongly excited by different types of earthquakes? A massive thrust fault, where one tectonic plate lurches beneath another, will efficiently generate modes that involve compression, while a strike-slip earthquake, where blocks of crust slide past each other, will more strongly excite the twisting toroidal modes. This seismic clock has provided some of our strongest constraints on the size and composition of Earth's core. The way certain modes split or change in frequency tells a clear story about the physical state of the iron-nickel core and the precise location of the boundary between the liquid outer core and the solid inner core. So we must ask, if we can listen to the resonant hum of our own world, what might the normal modes of Mars or Venus sound like? Could future missions plant seismometers on other worlds and tune into their unique planetary frequencies, revealing the hidden structures of alien landscapes? This celestial clock allows us to literally hear the heartbeat of our planet, a deep, resonant song that continues long after the ground has stopped shaking. Our planet has completed fewer than 20 full circuits around the galactic center in its entire 4.5 billion-year history. This is the Galactic Year, the ultimate celestial clock measuring time in units of our galaxy's rotation. Every 225 to 250 million years, our entire solar system finishes one majestic orbit around the Milky Way's core, a journey that carries us 1,000 light-years above and below the galactic plane. This immense timescale provides the fundamental rhythm for cosmic and geological processes, synchronizing events across the solar system as we voyage through vastly different galactic environments. Galactic dynamicists calculate this orbital period using our solar system's staggering speed of 220 kilometers per second and our distance of 26,000 light-years from the supermassive black hole at the galactic center. This combination of velocity and distance produces a single orbit so vast it defies human comprehension. The dinosaurs first appeared during one galactic year and vanished in the next, their entire dynasty lasting less than a single orbit. The exact length of this cosmic year is uncertain because we cannot precisely weigh the Milky Way's dark matter halo, whose invisible gravity is the dominant force guiding our path. As we travel, our orbital journey takes us through different galactic neighborhoods, from the sparse outer reaches to the crowded spiral arms dense with stars and molecular clouds. Each region presents a unique environment, with varying levels of cosmic radiation and gravitational perturbations that could influence our planet from afar. How many galactic years has Earth truly experienced since its fiery birth? And as we continue our endless loop, what will the next galactic neighborhood we visit be like, and how might its unique character shape the future of our world? This is the clock against which all other celestial timekeepers are measured, a grand orbit that frames the epic of life itself. Earth's magnetic field can lurch without warning. Deep beneath the crust, in the churning ocean of molten iron that forms the outer core, sudden pulses of energy send powerful tremors through our planetary shield. These events are geomagnetic jerks, abrupt shifts in the magnetic field's rate of change that rewrite the rules of our deep interior's clock. Unlike the slow, predictable rhythms of magnetic reversals, these jerks strike every few years, revealing a hidden world of rapid-fire dynamics. Scientists first identified these anomalies in the 1960s, puzzled by the sharp kinks that appeared in the smooth, decades-long records from magnetic observatories. The data told a clear story: the field's gradual drift would suddenly accelerate or decelerate in a matter of months. This was not a gradual process, it was a magnetic heartbeat, a jolt from the planet's core. The cause is thought to be hydromagnetic waves, pulses of energy that travel through the liquid core like tsunamis in an ocean of iron. These waves can rearrange the complex flow patterns of the molten metal, which in turn generates the magnetic field through a process called the geodynamo. When one of these waves reaches the boundary between the core and the solid mantle above, it can create a sudden, localized push, manifesting on the surface as a geomagnetic jerk. This is why their timing is so irregular. It reflects the turbulent, unpredictable storms within the core itself. The events of 1969, 1978, 1991, and 1999 stand out as particularly strong global jerks. Data from observatories from Honolulu to Helsinki showed nearly simultaneous changes in the field's behavior, a coordinated shudder that rippled across the entire planet. Other jerks are more regional, affecting only one hemisphere, which suggests the waves that cause them are more localized, perhaps bouncing off particular structures at the core mantle boundary. By studying the exact shape and timing of these jerks, core dynamicists can peer into conditions we can never visit. The speed and character of these events provide crucial clues about the core's physical properties, placing tight constraints on the viscosity and electrical conductivity of the molten iron. A more viscous fluid would dampen these waves more quickly, while a highly conductive one would allow them to travel faster and farther. So what does this mean for the magnetic shield that protects us? Each jerk is a sudden course correction in the field's long-term evolution. While a single event does not signal an imminent reversal, a cluster of powerful jerks could indicate a period of greater instability deep within the core, potentially leading to a more rapid decay of the field's protective strength. If the jerks begin to systematically weaken the field's intensity in key regions, the consequences for our technological world could be profound. How might our satellites and power grids fare if the next major geomagnetic jerk significantly weakens our shield just before a powerful solar storm? This hidden clock proves that the heart of our planet beats with a rhythm of sudden, decisive pulses, reminding us that the ground we stand on is merely the thin, quiet crust over a world of constant magnetic thunder. Our solar system possesses a hidden equator, an invisible plane of perfect balance around which the entire planetary system truly spins. This is the invariable plane, a fundamental disk of stability calculated from the sum of all motion within our cosmic neighborhood. While we often picture the planets orbiting within the flat sheet of the ecliptic, Earth's own orbital path, this is merely a local perspective. The invariable plane represents the solar system's true average angular momentum, a reference frame so stable it remains virtually unaffected by the constant gravitational jostling between planets. To find it, celestial dynamicists perform a grand calculation, summing the individual angular momentum vectors of every significant body, from the Sun itself to the most distant dwarf planets. The result is a single, unwavering plane that acts as the ultimate background grid for the solar system. Jupiter, the solar system's gravitational heavyweight, dominates this calculation, contributing a staggering 60% of the total angular momentum due to its immense mass and rapid orbital speed. This Jovian dominance means the invariable plane is tilted by about 1.5 degrees from the Sun's own equator, a permanent testament to the king planet's influence. This stable plane is not perfectly frozen in space, however. Over immense timescales, the invariable plane itself undergoes a slow precession, a gradual wobble induced by the subtle gravitational tugs from passing stars and the overall mass of the galactic disk. This precession is exceptionally slow, taking millions of years to complete even a tiny fraction of a cycle, making it one of the most ponderous clocks we have encountered. Why is this abstract plane so crucial for astronomers, for studies of the solar system's most distant and enigmatic inhabitants, the trans-Neptunian objects and comets in the Oort cloud? The invariable plane provides the most natural and stable coordinate system. Their orbits, often wildly inclined to the inner planet's ecliptic, make far more sense when plotted against this fundamental plane of rotation. This concept is closely related to the Laplace plane, the average plane around which a satellite's orbit precesses. For objects in the outer solar system, the Laplace plane smoothly transitions from being dominated by the Sun's gravity to being shaped by the galactic tide, and the invariable plane sits at the heart of this transition. As the solar system continues to age, how will this fundamental plane evolve? Over the next several billion years, as planetary orbits gradually migrate and interact, the balance of angular momentum will slowly shift. Could a gravitational dance between the giant planets one day alter the tilt of this cosmic table? This systematic clock provides the silent, stable stage upon which the more rapid dances of the planets unfold, a fixed direction in space that will long outlive every world in our solar system. The air itself holds a hidden momentum, a global spin that tugs on the very length of our days. This is the atmospheric angular momentum cycle, a celestial clock where the planet's weather and its rotation are locked in a constant exchange of energy. Climate scientists and Earth rotation experts discovered this intimate link in the 20th century, realizing that the planet's spin is not just a simple constant, but a dynamic conversation with its own atmosphere. The key lies in the powerful rivers of air known as the jet streams. These zonal winds flowing from west to east carry immense angular momentum. When these winds accelerate, they can act like the extended arms of a spinning ice skater, slowing the planet down by a tiny fraction. Conversely, when the winds slow, that momentum is transferred back to the solid Earth, causing it to spin a little faster. This transfer happens in two main ways: through the brute force of mountain torque, where winds slam into massive ranges like the Rockies or the Andes, and through surface friction, where moving air drags against the land and sea. The most reliable tick of this clock is the seasonal cycle. Every northern hemisphere winter, the temperature contrast between the pole and the equator intensifies, supercharging the mid-latitude jet streams. This atmospheric acceleration steals a minuscule amount of the Earth's rotational momentum, measurably lengthening the day. The data from the International Earth Rotation and Reference System Service shows this correlation with stunning clarity, a repeating annual heartbeat in the planet's spin. But there are slower rhythms too. The El Niño Southern Oscillation, a climate pattern that rearranges heat and wind across the Pacific, leaves a distinct signature in the length of day records. During a strong El Niño event, changes in global wind patterns can alter the Earth's rotation by a few tenths of a millisecond, a tiny but detectable shift that integrates the entire planet's weather into a single, precise rotational parameter. This forces us to look both forward and back. As human-driven climate change alters global wind patterns and intensifies the jet streams, how will it affect this delicate balance? Will a warmer world lead to a systematically slower spin over centuries? And looking back into deep time, what would the rotational signature of a hothouse Earth or a snowball Earth have been? Could the dizzyingly fast spin of a young planet with its 18-hour days have been partly sustained by a vastly different atmospheric circulation? This atmospheric clock proves that the air we breathe and the time we live by are part of a single, interconnected system, where a storm gathering over an ocean can ultimately change the speed of the world. The moon offers us more than just its familiar face. A patient observer will notice it appears to wobble, rocking gently back and forth in a slow, rhythmic dance. This phenomenon is called lunar libration, a celestial clock that, over time, reveals 59% of the lunar surface from our earthly vantage point, all without us ever leaving our planet. These subtle oscillations arise from the complex geometry of the moon's elliptical path and its slight axial tilt, creating a clockwork of shifting perspectives with cycles ranging from a single day to many years. The three types of libration work in concert. Libration in longitude occurs because the moon travels faster in its elliptical orbit when it is closer to Earth and slower when it is farther away. This variation in speed allows us to peer slightly around the eastern and western edges as it rocks forward and back. Libration in latitude happens because the moon's axis is tilted relative to its orbit around Earth, letting us see over its north and south poles at different times. Finally, diurnal libration is a daily effect caused by Earth's own rotation, giving an observer on the sunset or sunrise horizon a slightly different angle on the lunar sphere as the night progresses. For lunar astronomers, these motions are not mere curiosities. They were systematically mapped as early as the 17th century, and they provided the very first glimpses of the moon's mysterious far side long before the space age. As the moon librated, slivers of the hidden hemisphere would swing into view along the limb, allowing cartographers to painstakingly piece together a map of the unseen. One of the most spectacular discoveries made this way was Mare Orientale, a vast bullseye-shaped impact basin that remained nothing more than a hint of a wavy ridge until libration revealed its full structure. Today, precise measurement of these wobbles is a powerful tool for celestial mechanicians. By tracking the moon's subtle rocking with laser ranging, scientists can probe the interior structure of our companion, testing models of its density and the state of its core. How might future lunar colonists use this knowledge? For settlers living on the moon's surface, these libration cycles would be a fundamental part of their celestial navigation. A predictable rhythm in the sky that would tell them exactly when Earth would dip into view from the limb of their crater home, or when a particular landmark on the distant Earth would become visible. This intricate dance reminds us that even a world that seems locked in a silent embrace is constantly in motion, offering us hidden vistas through the patient ticking of a geometrical clock. Even the most precise cosmic clockwork harbors a deep and fundamental unpredictability. the long-term future of our solar system dissolves into a haze of uncertainty beyond 50 or 100 million years, not for lack of data, but because of the chaotic mathematics of gravity itself. This is the solar system's chaos timescale, a celestial clock that measures the limit of our foresight. Dynamicists who run supercomputer simulations of planetary motion have discovered that our familiar planetary orbits are not eternally stable and predictable. They are, in fact, chaotic systems where tiny, immeasurable differences in the starting conditions grow exponentially over time, rendering any precise prediction of planetary positions impossible after a certain point. The primary driver of this chaos is a complex web of weak gravitational resonances between the planets. Every time one world completes a certain number of orbits, it gives another a tiny, repeated gravitational nudge. These nudges are minuscule, but over millions of years they can add up in unpredictable ways, like a pencil balanced on its point that eventually falls in a direction determined by an imperceptible draft. The most vulnerable world is Mercury, whose small mass and elliptical orbit make it susceptible to being shaken by the giants, particularly Jupiter. The French astronomer Jacques Lascar's detailed numerical simulations have shown that Mercury's orbit has a small but real chance of becoming so eccentric over the next several billion years that it could potentially cross the path of Venus, leading to a catastrophic collision or ejection from the solar system. This chaos does not mean the planets will fly apart tomorrow, or even in the next 10 million years. The solar system is metastable, like a ball resting in a wide, shallow bowl. It can wobble and roll around for an immense amount of time before a chance accumulation of nudges sends it over the edge. But this inherent limit profoundly affects our ability to peer into Earth's deep past. When paleoclimatologists try to use Milankovitch cycles to explain climate changes from 200 million years ago, they hit a wall. The astronomical solutions, the precise calculations of Earth's orbital variations, become meaningless that far back because the chaotic evolution of the inner solar system makes it impossible to know Earth's exact orbital configuration. The very clock we use to explain ice ages becomes unreadable in the distant fog of time, so we are left with a humbling cosmic truth. How can we ever build a complete history of Earth's climate when the primary astronomical driver becomes fundamentally unknowable beyond a certain point? This chaotic clock teaches us that the universe is not a perfect, predictable machine, but a dynamic and inherently uncertain system, setting an ultimate boundary on our quest to forecast the celestial future. Deep within the planet, a hidden world spins to its own rhythm. Earth's solid inner core, a ball of iron nickel the size of the moon, rotates slightly faster than the rest of the globe, gaining a fraction of a degree on the mantle and crust each year. This phenomenon, called inner core superrotation, is a differential spin that creates a fundamental clock ticking at the very heart of our world. The discovery of this motion was a triumph of seismic listening. Seismologists noticed that the travel times of earthquake waves passing through the core changed subtly over the decades. By analyzing waves from repeating earthquakes in the same location, they detected a consistent shift, a pattern that could only be explained if the inner core was rotating just a little bit faster than the mantle above it. This superrotation is driven by a powerful electromagnetic lock. The magnetic field generated by the churning motion of the liquid outer core grips the solid inner core, trying to drag it along. Because the outer core's fluid dynamics are complex and somewhat independent of the mantle's rotation, the inner core gets pulled ahead in a slow, perpetual race. The rate of this spin is not perfectly constant. Core dynamicists believe it fluctuates over time, perhaps in response to the turbulent flows in the outer core or changes in the strength of the magnetic field itself. These variations provide a crucial clue about the physical conditions at the inner core boundary, a place of unimaginable heat and pressure. The viscosity of the material there, how easily it flows or deforms, directly influences how easily the inner core can slip past the surrounding liquid. This differential motion is far more than a geological curiosity. It is a direct driver of the magnetic field's behavior. The superrotation contributes to what scientists call the secular variation, the slow drift and wobble of the magnetic poles over years and decades. The constantly shifting position of the inner core relative to the mantle helps to shape the intricate patterns of magnetic flux that erupt onto the planet's surface and extend out into space. What would happen if this deep Earth clock were to slow or stop? How might a change in the superrotation rate have influenced the magnetic field's strength during past reversals, those times when the north and south poles flipped? The inner core's silent spin reminds us that our planet is not a single, solid body, but a set of nested spheres, each moving to its own rhythm, all working in concert to generate the protective shield that makes our world a home. This ghostly sea of particles is the oldest timepiece in existence. Billions of these cosmic messengers pass through your body every second, a silent whisper from the universe's first moment of consciousness. They form the cosmic neutrino background, a relic radiation born when the cosmos was just 1 second old, while the cosmic microwave background shows us the universe at 380,000 years. This neutrino sea captures a snapshot from a far more violent and primordial age. In that first second, the universe was a dense, hot soup of fundamental particles, neutrinos which interact only through the weak nuclear force and gravity, were constantly colliding with everything else. But as the universe expanded and cooled in that frantic first second, it suddenly became too sparse for these neutrinos to find anything to collide with. They decoupled from the rest of matter, flying free and preserving a perfect fingerprint of the universe at that exact instant. Their energy has been fading ever since, stretched by the expansion of space itself. Cosmologists calculate their present temperature must be about 1.95 Kelvin, just slightly colder than the cosmic microwave background. We have never detected them directly because their energy is impossibly low, but we know they must be there, a foundational prediction of our standard model of cosmology. Their indirect influence, however, is written across the sky. This primordial fog of neutrinos shaped the large-scale structure of the universe. In the earliest epochs, these particles moved at nearly the speed of light. Their relentless streaming actually smoothed out some of the initial clumpiness of matter, suppressing the formation of the very smallest galaxies. The patterns we see in galaxies today, the vast cosmic web, bear the imprint of this neutrino drag. Everything we have built, every star and planet, formed in a universe whose architecture was subtly sculpted by this invisible background sea. Detecting these specific neutrinos directly is one of the ultimate goals of modern physics. The challenge is almost beyond comprehension. To catch one, a detector would need to be unimaginably massive and perfectly shielded, as these ancient particles interact so feebly that they pass through entire planets like light through glass. Current experiments can detect neutrinos from the Sun or from supernova, but those have millions of times more energy than the primordial ones we seek. Finding a way to observe this background would open a window directly into the first second of time, letting us test physics at energies far beyond what any particle collider on Earth could ever reach. It would tell us if neutrinos have a tiny mass, a property that would have subtly altered their flight and changed how they painted the cosmic canvas. What ultimate secrets are frozen into this signal? Could it reveal details about the hypothetical inflationary epoch, a split second of hyper-expansion that predates the neutrino background itself? This celestial clock connects us to the very dawn of time, a ticking heartbeat from the moment the cosmos first began to take shape. Our journey through the cosmos reveals a universe not of random chaos, but of profound and intricate order. We have moved from the grand, slow wobble of our planet's axis to the frantic heartbeat of solar storms, from the moon's patient retreat to the silent rain of galactic cosmic rays. Each of these 25 celestial clocks and the many supporting rhythms we have explored ticks to its own unique cadence, yet they are all interconnected threads in a single, magnificent temporal tapestry. Time in our universe is not a simple, linear river, but a symphony of cycles, from the millisecond variations in Earth's rotation to the billion-year orbits around the galactic core. These cosmic timekeepers have been the unseen conductors of Earth's entire history. They have opened and closed the great ice ages, guided the monsoon rains that fed ancient empires, and set the environmental stage upon which life itself evolved and adapted. The profound implication is inescapable. To truly understand our planet's past and to anticipate its future, we cannot look only at the ground beneath our feet. We must lift our gaze to the cosmic environment in which we are embedded, a dynamic system of gravitational harmonies and celestial mechanics that has always governed our world. The giant planets tug at our orbit, the sun's magnetic mood swings alter our upper atmosphere, and the very structure of the galaxy may have timed the arrival of comets that changed the course of life. As our technology advances with more powerful telescopes and more sensitive instruments, we move closer to reading this grand celestial clockwork with ever-increasing precision. We are learning to listen to the hum of the cosmic neutrino background and to measure the subtle drift of the inner core. This is not the end of discovery, but a new beginning. So the next time you look up at the night sky, see it not as a static picture, but as a dynamic, ticking face of a clock with 25 hands, each moving at its own impossible speed. Which of these cosmic timekeepers captured your imagination the most? Was it the patient great year of precession, the solar system's chaotic future, or the silent pull of the galactic tide? Share your thoughts and keep